So we looked at rules for multiplying and dividing complex numbers in polar form. We also have a rule for powers of complex numbers. Now it's really not all that different. Keep in mind when you take something to a power, you're really just multiplying it by itself a number of times. So this theorem, it's called DeMoivres theorem, is useful for finding powers of complex numbers, but it really comes from that product idea. So remember, when multiplying two complex numbers, we multiply the moduli. Well, we're about to do the same thing. If I'm taking a complex number to a power, I'm just going to take that modulus to a power. And then, when we were multiplying complex numbers, we added the arguments. Well, now I'm going to be adding that same argument over and over and over again. Repeated addition is just multiplication. So I'll have cosine times n theta, cosine of n theta, plus I sine of n theta. So in short, we're going to raise the modulus to whatever that power is, and then we're going to multiply the argument. So it's a bit quicker than the multiplication and the division problems in that we only have to worry about one theta, we only have to worry about one r. So they do go by pretty quick. Let's go ahead and let green be the modulus, and we'll let blue be our theta here. We'll let the power be red. Oh, zooming in doesn't work. All right. So we want to raise this complex number to that power. So keep in mind that means I'm taking my modulus, which in this case is 2. I'm going to raise 2 to the 4th power. We'll clean that up momentarily. I also need to take cosine of 4 times my angle and I sine of 4 times the angle. So that's our DeMoivres theorem. We can clean this up. 2 to the 4th power. Hey, that's something we can handle. That's 2 times 2 times 2 times 2, which is just 16. Cosine of 4 times pi over 3, well, that's just cosine of 4 pi over 3. And then we also have that same argument for I sine. Don't really need those parentheses. Now, if we take a look at the instructions here, they do ask us to write this in rectangular form. Had they have just asked us for polar form, this would be done. But they did ask us for rectangular form, so we need to go one step further. Keep in mind, in order to go from polar to rectangular, it's just a table lookup, in particular a unit circle. Unit circle lookup to get those cosine and sine values. And then we also have that distributive property. So we know we're going to have a 16. We know we're going to have that I. And then a couple of table lookups, cosine of 4 pi over 3 and sine of 4 pi over 3. So jumping back here to our unit circle for 4 pi over 3. That is located conveniently way down here. So we want the negative 1/2 and the negative root 3 over 2. Whoop, everything got tiny again. So 16 times negative 1/2, and then we also have a 16 times root 3, pardon, negative root 3 over 2. Let's go ahead and zoom back in. So cleaning this up a little bit, 16 times negative 1/2, that will be negative 8. Then when we jump over to the right half, know that there is a little negative sign here. So we'll have negative, same thing, 16 divided by 2 is just 8. We still have an I in that right term, and then also a root 3. So that is our rectangular form. Keep in mind, when they ask for rectangular form, we do need to go that extra step there. So we'll take a look at one more of these. It's already in polar form, and then we'll also take a look at some that start off in rectangular form. So jumping over to the far right example here. So using the same colors here, we'll go ahead and let the modulus be green, the angle be blue, and the exponent be red. So DeMoivres' theorem here, we want 4 to the 6th power. You might need to use a calculator to find that, no harm, no foul. And then we also want cosine of 6 times pi over 4, and I sine of 6 times pi over 4. So cleaning this up, 4 to the 6th power will be 4,096. And then jumping into the parentheses here, note that I have a 6 times pi over 4. So 6 and 4 do have that 2 in common. So that will be 3 pi over 2. So we're going to have a cosine of 3 pi over 2 and an I sine of 3 pi over 2. So these are just quadrantals. 3 pi over 2 is the same as 270 degrees. So cosine of 3 pi over 2, that's when we're looking straight down in our unit circle. So cosine is going to be 0 there. Sine of 3 pi over 2, that's just -1. Again, you can jump over to the unit circle for that if you like, but we don't really need to in this case. So when we go to distribute, you'll have 4,096 times 0. Yep, that's 0. And you'll also have 4,096 times -I. So that will give you a negative 4,096 I. So this is using DeMoivres' theorem. It is fairly quick. I would argue that it's actually a bit quicker than multiplication because you only have one angle to worry about. The one thing that can throw us for a loop here is if we are not given polar form. So we'll look at a couple examples where we're not given that polar form to start with.